Imagine a journey from Shanghai to Los Angeles in less than 30 minutes, or completing a full orbit around the Earth in just over 2 hours. While this may sound like the stuff of science fiction, it could become a reality sooner than expected, thanks to China's breakthrough in hypersonic propulsion technology. Chinese scientists have successfully tested the world's first oblique detonation engine powered by standard aviation kerosene, achieving speeds of up to Mach 16, or approximately 19,600 kilometers per hour. This extraordinary development could revolutionize both air and space travel, bridging the gap between atmospheric flight and space exploration. For years, engineers have faced the challenge of creating an engine capable of maintaining hypersonic speeds without relying on conventional propulsion methods. China's oblique detonation engine offers a groundbreaking solution. Unlike traditional scramjet engines, which depend on subsonic combustion within a supersonic airflow, the OD engine uses shock waves to ignite fuel. This mechanism allows for more efficient and stable combustion at extreme speeds, drastically reducing one of the most significant risks in hypersonic propulsion, flameouts. At the heart of this breakthrough is the use of standard aviation kerosene, a first for hypersonic engines. Traditionally, hydrogen-based fuels have been used for such high-speed engines due to their quick ignition properties. However, hydrogen is notoriously difficult to store and transport, making it impractical for real-world applications. China's solution involves precompressing RP3 fuel to an astonishing 3,527 psi before ignition, allowing it to burn quickly like hydrogen, but with the added benefit of easier handling. Another key innovation is the engine's combustion chamber design. Engineers have incorporated a 5 mm bump inside the chamber that triggers a self-sustaining detonation wave, stabilizing the combustion process. This design eliminates the need for the large, cumbersome combustion chambers typically required in scramjets, making the OD engine's combustor 85% shorter. The result? Lighter aircraft, longer flight ranges, and improved fuel efficiency, all critical elements for practical hypersonic applications. The engine was tested in Beijing's JF-12 shock tunnel, one of the world's most advanced hypersonic research facilities. The tunnel simulates real flight conditions at altitudes above 40 kilometers. During testing, the engine maintained detonation at Mach 9 over a distance of 1,550 meters within the 50-millisecond test window. While the test duration was brief, it demonstrated that the engine could sustain combustion under extreme conditions, an essential milestone. The implications of this technology are profound. A fully developed OD-powered aircraft could fly from Shanghai to New York in under 40 minutes, effectively bridging the gap between atmospheric flight and space travel. If scaled up, this technology could lead to reusable spaceplanes, making low-cost orbital access a feasible reality. The strategic advantages of China's oblique detonation engine are immense. If deployed in hypersonic aircraft or weapons, it could reshape modern warfare by outrunning every existing defense system. At speeds of Mach 16, missiles, drones, and bombers powered by this technology would be nearly unstoppable, striking targets before enemy defenses even have time to react. To put this into perspective, the current hypersonic missiles of the United States and Russia operate at speeds between Mach 5 and Mach 10 and have limited maneuverability. In contrast, China's OD-powered vehicles would travel at nearly twice the speed, making interception all but impossible. A missile launched from China at Mach 16 could reach any point on Earth in under an hour, dramatically reducing the response time for adversaries. The fuel efficiency and operational range offered by the OD engine are also key advantages. Since it uses standard aviation kerosene, China avoids the logistical difficulties associated with hydrogen fuel storage. This means China could mass-produce hypersonic aircraft and missiles without the infrastructure constraints faced by the US and Russia. The reduced operational costs would make these weapons more deployable, giving China a strategic edge in prolonged military engagements. However, hypersonic dominance is not just about speed. It's also about survivability. Traditional intercontinental ballistic missiles follow predictable, ballistic paths, making them easier to intercept with anti-missile defense systems. Hypersonic weapons, on the other hand, can change course mid-flight, rendering current defense technologies largely ineffective. If China successfully integrates OD-powered hypersonic missiles into its arsenal, these weapons could bypass existing missile defense systems, forcing other nations to reconsider their entire defense strategies. This development also contributes to the growing hypersonic arms race between China, the US, and Russia. While the US has faced significant setbacks in developing scramjet-based hypersonic weapons, Russia has made notable progress with its avant-garde hypersonic glide vehicle, which can reach speeds of Mach 20. However, the avant-garde still relies on traditional ballistic missile technology, whereas China's OD engine opens the door to sustained atmospheric hypersonic flight, offering greater flexibility and range. China has publicly announced its goal of developing an operational hypersonic aircraft by 2030. Despite this impressive breakthrough, substantial engineering challenges remain before Oblique detonation engines can achieve full operational capabilities. The 50-millisecond test in the JF-12 shock tunnel confirmed the engine can work in controlled conditions, but sustaining hypersonic combustion over long distances and extended flight durations requires further development. Thermal management presents one of the primary challenges. At Mach 16, the friction generated by atmospheric particles creates extreme heat, potentially exceeding 3,500 degrees Celsius. Traditional aircraft materials would melt under these conditions. New heat-resistant alloys and active cooling systems must be developed to prevent structural failure. China will need to advance materials science to withstand these extreme temperatures without degradation over time. Fuel delivery and efficiency also present engineering hurdles. While the precompression technique used to ignite RP3 kerosene works in laboratory conditions, integrating this into a real-world aircraft engine presents challenges. Ensuring stable fuel flow at hypersonic speeds without disrupting the combustion process is critical. Even minor fluctuations in airflow or fuel mixing could destabilize the detonation wave, leading to power loss or catastrophic failure. Another significant concern is pilot control and human survivability. At speeds of Mach 16, maneuvering an aircraft becomes incredibly difficult due to extreme g-forces. Even with artificial intelligence systems handling navigation, communication delays at such speeds could complicate real-time decision-making. Hypersonic reconnaissance and transport missions might require fully autonomous flight systems, an area still under development. However, if these challenges can be overcome, the potential civilian applications are transformative. Imagine commercial hypersonic travel where flights between New York and Tokyo take less than an hour. Space agencies could use this technology to develop reusable spaceplanes, drastically lowering launch costs and making space exploration more accessible than ever before. While China's 2030 goal for a hypersonic aircraft may seem ambitious, the progress made thus far suggests it is not unattainable. With continued advancements in aerospace materials, AI, and fuel systems, this new era of hypersonic travel could become a reality sooner than expected. China's successful testing of the Oblique detonation engine marks a major milestone in hypersonic propulsion technology. By utilizing standard aviation kerosene to achieve speeds up to Mach 16, this innovation has the potential to transform air and space travel, offering unprecedented speed and efficiency. While significant technical challenges remain, the progress made so far highlights a future where the lines between atmospheric flight and space exploration become increasingly blurred. As research and development continue, the dream of traversing vast distances in mere minutes moves closer to reality, heralding a new era in aerospace capabilities. As China's hypersonic propulsion technology continues to evolve, the implications for both military and civilian travel are immense. With the potential to drastically reduce travel times and revolutionize space exploration, this breakthrough could forever change how we think about speed and accessibility. However, the question remains, will this technology be the key to shaping the future of global transportation? Or will the challenges it presents, such as fuel efficiency and heat management, prevent it from becoming a practical reality? As we approach the dawn of this new era, it's clear that the race to develop the world's fastest hypersonic engine is only just beginning. How soon will we see these revolutionary planes and spacecraft in our skies, and how will they reshape our world?